recording. Okay, so today is calculating limits, meaning we will solve limits by hand today, which is great. No calculator needed unless we absolutely cannot figure out the limit. So first up is a page of limit laws or limit properties. And these are all the algebraic properties that we can apply to limits, since calculus is heavily algebra based. So let's go over number 1. This says the limit as x approaches some number a of a constant k will be the constant. So the limit of a constant is the constant. So, and I'll do examples of these as well. So for number 1, just to have an example of it, if I said the limit as x approached some number a of 5, what would the limit of 5 be?
5.
That's it. The limit of 5 would be 10. Would be 10. The limit of 5 would be 5. So it doesn't matter if it's 10, 15, 100, 1000. The limit of a constant will always be a constant. And remember what it means to be a constant. To be a constant means that it's just a number without a variable. That's what a constant is. Okay. Number 2, the limit as x approaches a of x is equal to a. So this is actually called the direct substitution process or property, because all this limit's saying is, hey, take a and plug it in for x, and you'll get your limit. So to do an example of number 2, if I said the limit as x approached 3 of x, what would my limit be?
3.
3. Good. That's it. That's how that works. Just plug that number in for x. Okay. Number 3. This says the limit as x approaches a of f of x plus or minus g of x can be split into the limit of f of x plus or minus the limit of g of x. So what we're saying here is that the limit can be applied to multiple terms connected by addition or subtraction. So for this example, or this property, you had 2 terms inside, which means we'll have 2 limits. If there's more than 2 terms, then you'll have more limits. So a good example of this one is, let's just say I had the limit as x approached a of x plus, let's just say, x squared. Applying property 3 means I can just rewrite this as the limit as x approaches a of x plus the limit as x approaches a of x squared. So this property just allows me to expand it over addition or subtraction. So it could have been negative as well. It could have been minus, and the properties would still work. Okay. 4 says the limit as x approaches a of some constant k times f of x will equal that constant k times the limit of f of x. So all this property says is if you have a coefficient in front of a function, take that coefficient and move it to the front of the limit. So to represent number 4, a good example, let's just say I had the limit as x approached a of 5x squared. All property 4 says is, hey, take that 5 and move it to the front. 5 times the limit as x approaches a of x squared. That's it. You can just rewrite it like that. Okay. Let's zoom out a bit. 5 is just like number 3. You can apply the limit over multiple terms, except this time it is the product of 2 terms. So for number 5, it says the limit as x approaches a of f of x times g of x is equivalent to the limit of f of x times the limit of g of x. So you can apply it over multiplication as well. So for number 5, let's do another example. The limit as x approaches a of, let's just say, x plus 1 times x plus 2. I can rewrite this. Nice. I want to be where that party's at. Fiesta is until April, though. Okay, guys? If we're going to have a fiesta. And I can split this into 2 limits. So I'll have the limit as x approaches a of x plus 2. So I was just able to apply this limit over multiplication into multiple terms. So once again, 2 terms, 3 terms, n amount of terms, you'll have n amount of limits. All right. Will COVID go away so we can enjoy Fiesta? Probably not. It's my favorite time in San Antonio, though, guys.
Best time to get COVID, too.
There you go. And get roasted corn while getting COVID, okay? It will be worth it. Okay. 6 is just like 3 and just like 5. I was going to say 6, but we're doing 6. The limit can be applied over division. So the limit of f of x over g of x can be split into the limit of f of x over the limit of g of x. So for number 6, another example to represent that, we would say the limit as x approaches a of, how about, x over x plus 1. And I can rewrite this as the limit as x approaches a of x over the limit as x approaches a of x plus 1. So you can just apply the limit to the numerator and the denominator. Hey, was it Nacho Libre? Hey, save me a piece of that corn.
Get that corn out of my face.
Get corn out of my face. And this is a crazy lady. All right. Moving on. Great movie. All right. Number 7 says if you have the limit of a power function, f of x to the n, you can apply the limit inside the parentheses. So for number 7, what could I say? The limit as x approaches a of x plus 1 to the 5th power can be rewritten as the limit as x approaches a of x plus 1 to the 5th. Okay. And then number 8 is just like number 2, direct substitution. The limit as x approaches a of x to the n can be rewritten as a to the n. So again, you would just plug in whatever number you had for x, or whatever number the limit was approaching. So don't really need an example for 8 or 9, because 8 and 9 are just like number 2. The 9 says the limit as x approaches a of the nth root of x is equal to the nth root of a. So again, whatever number that x is approaching, you'll plug in for x and simplify your limit. And number 10 says the limit as x approaches a of the nth root of f of x. This allows you to apply the limit inside the radical. So this would become the nth root of the limit of f of x. So I can write an example for that one. Number 10, we could just say the limit as x approaches a of the 5th root of x. Any root, 5th root, 6th root, even root, odd root, doesn't matter. You can rewrite it as the 5th root of the limit as x approaches a of x. So that limit can just go inside the radical. Okay, and this works for double-sided limits. This works for limits to the left and also limits to the right. Okay, so those are all the algebraic properties for limits. So let's go ahead and evaluate these limits, justifying each step by the properties above, and then never ever do this again. So this first example is just to show you how the properties work. So we have for number 1, the limit as x approaches 5 of 2x squared minus 3x plus 4. So what I want to do is expand this by the limit properties. So if I expand this, how many limits will I have?
3.
3. Good. So this will become the limit as x approaches 5 of 2x squared minus the limit as x approaches 5 of 3x plus the limit as x approaches 5 of 4. Okay. And now let's go ahead and apply more properties from the above. And where can I move this to? And where could I move that 3? To the front of the limit, which means you get 2 times the limit as x approaches 5 of x squared minus 3 times the limit as x approaches 5 of x plus the limit as x approaches 5 of 4. Okay. And now all that is left is plugging in what number for x?
5.
5. So this will become 2 times 5 squared minus 3 times 5. And the last one's going to use the very first property, the limit of a constant. What is the limit as x approaches 5 of 4?
4.
4. There you go. And now simplify everything. What's that? 2 times 25, that's 50 minus 15 plus 4. That is, what is our final limit?
39.
39. Okay. And that's how you apply the limit properties step by step by step. Oh, but do I have a treat for you so we never have to do this again? What number could we have plugged in from the very beginning?
5.
5. And we would have been right here. Done deal. But that wasn't the purpose of the exercise. The purpose of the exercise was how can you use the properties above that you just learned? And now that you know how to use these properties, you know you can use them whenever you want, but all you really have to do is plug in 5 and solve. So, not bad, right? Which means that for the next one, instead of doing all that work, for number 2, we have the limit as x approaches -2 of x cubed plus 2x squared minus 1 over 5 minus 3x. Go ahead and just plug in what number? -2. Perfect. I'm just going to rewrite it to be neat. And we're going to plug in -2 now. -2 cubed plus 2 times -2 squared minus 1 over 5 minus 3 times -2. Now, isn't that so much easier than justifying each step? Yeah, sure. All right, cool. All right, so you get -8, and then what's that? 4 is that 8 minus 1 over 5 plus 6, 11. So what's my final answer? -1/11. There you go, guys. So we have an example where we can justify a limit step by step by step. And then we have a limit where it's like, hey, just plug it in. No need to justify anymore if you know what you're doing. So any questions on that?
So
Sounds easy enough.
Sorry. I was going to
Okay.
say on the homework, so we don't really have to justify as long as we know what we're doing, right?
Yeah. Well, if the homework says justify, then I want you to show the steps. I mean, I
Mhm.
think you only have like what, 1 or 2 questions that say that.
Oh, okay. Oh, I'm sorry. Would it be okay if I ask a question kind of related to the homework we have today?
For which section? For this homework?
I think it was 1.1. It was number 5 specifically, but it's not that I didn't understand the math. It's I think because it's the one problem I haven't done. I did everything else.
Okay.
I think the way
Well,
that it reads, I think I misread it. Like I
okay.
was making it harder for myself.
All right. Well, since I started lecture, I'm going to finish lecture and there'll be time for questions. But if you can't hang out till then I think, if anything, I can get you in a breakout room with Ryan so you guys can work on it.
Okay, thank you.
So you want to prefer that instead?
Sure. Cause yeah, I'm okay with that.
I don't want to do it. No, I'm just kidding.
More, I'll make Ryan a co-host and then, oh boy, here we go. Yes, and then I can do a breakout room and then I'll assign manually 1 breakout room and then I'm just
It's
gonna.
weird to see Ryan actually doing something during the class.
Ooh,
Dang.
I know, right?
I know who not to give advice on the electrical engineering path.
Dang.
Oh,
Dang it.
I mean, what?
All right, Ryan and Serena, and off you go.
Thank
Yeah?
you.
There you go. Cool. All right. All right, cool. Everybody else is still here, right?
Still here.
Okay. All right, they're in the breakout. Okay, I'm making sure I didn't lose anybody. Anybody else?
Professor C, I have
Yes.
a question.
What's up?
So for number 1, couldn't we have factored it or
Um,
back on?
if you can factor it, that's good. Factor it, but either way, you're still going to plug in 5.
Okay.
Yeah. Well, that's a good question. So yeah, I mean, I want you guys to notice that for a simple polynomial like number 1, you don't actually have to factor it. You just plug the number in. But once we get into rational limits like number 2, if you can factor the numerator, then factor it automatically. So, because if you do, it's going to help you simplify the limit a lot easier. Okay. But any other questions on this page?
They're not all like this, right? You can just plug it in. They're not all like this.
Oh yeah, for a limit, one of the easiest way to evaluate a limit is to plug in the number. Yeah, so maybe calculus is too easy for now, right?
I was gonna say this calc class sounds too easy.
Because this next page brings us up to the direct substitution property, what I've been talking about. It says, if you have a polynomial or rational function and a, the number we're plugging in, is in the domain of that function, then all you have to do is plug in a for x, which is what we've been doing, right? So polynomial functions are all go. You'll plug in that number and you'll simplify. Rational functions, we must be careful on plugging any number in. And we'll see that on these next 2 examples. So for number 3, we're going to apply this direct substitution property like we've been doing. This says the limit as x approaches pi of x times the cosine of x. Now, since this is a polynomial function, what am I going to plug in for every x?
Pi.
Pi. Good. And of course, I'm just going to write it over. And I'm going to plug in pi for x. So I'm going to get pi. That's ugly pi. But that's how all my pi's look. All right. Pi times the cosine of pi. And I'm going to get pi times. And who knows what cosine at pi is?
-1.
-1. Very good. So my answer for this limit is negative
Pi.
pi. There you go. So for any polynomial function, plug it in and let's get on with our day. Everybody good with that? right. So number 4, let's go ahead and use that same process. You have the limit as x approaches 1 of x squared minus 1 over x minus 1. And what number are we going to plug in for x?
1.
No.
1. So let's go ahead and plug 1 in for x. And what is going to happen here?
Zero. That weird word you said yesterday? Inter.
Intergalactic, yes. So you're going to get 0 over 0, which if I did mention it last time, then this is called an indeterminate form. Indeterminate, which means that we have to go back to the very first step and see how we can fix it. So if you ever get indeterminate, 0 over 0, come back to the original limit and let's analyze it and see if we can fix it algebraically. And like I said, keep your mind fresh and algebraic. What do you notice about the numerator?
Difference of squares.
It's a difference of squares, which can be, what's that favorite F word of yours?
Factored out.
Factored out. So what is x squared minus 1 factored to?
X plus 1, x minus 1.
There you go. And then on this step, what's going to happen?
Cancel x minus 1.
X minus 1's cancel. And then we get the limit as x approaches 1 of x plus 1. And is it now safe to plug in 1?
Yes.
Yes, which means if we plug in 1, what is our limit value?
2.
2. Now 2 looks very different from 0 over 0, right? So
Yes.
if you ever come across an indeterminate form, you must fix it. And if you can't fix it algebraically, well then that's why we had, what's today, Wednesday? That's why we had Monday's lesson on how to solve a limit by using a calculator. If you've exhausted all algebraic thoughts, operations, you can't do anything about it, whip out that calculator and make an XY chart. Okay.
You can never have indeterminate form like an answer.
No, we can never have indeterminate for an answer. You can always fix an indeterminate form. You cannot fix an undefined form.
Got it.
All right. Okay. So that's direct substitution property. If it's a polynomial, plug it in. If it's a rational, plug it in, see if it still works. If it doesn't, go back and see if you can fix it by factoring or some other algebraic method. Okay. The little sentence below, it says fact. If f of x equals g of x when x can equal a, then the limit is f of x equals g of x provided the limit exists. Basically, what that means is that when the limit doesn't exist, when you get an indeterminate form, you go back, factor, and reduce the function. So f of x becomes g of x, the reduced function, and on that reduced function, the limit will exist, such as we did in number 4. We first attempted the original function and got 0 over 0. Then we reduced the function. It becomes g of x now, the reduced function, and the limit exists. But no matter what, the limit for this original problem is still going to be 2. That's all that says. Okay. Yes. Now, remember these lovely properties. You guys remember these from Monday?
Yes.
These are our trig, we'll call them our trig limit identities, because if you ever see the limit as x approaches 0 of sine x over x or x over sine of x, that limit is always going to be 1. And since we're here, I'll also throw in these special treats for you as well. the limit as x approaches 0 of tangent x over x will be 1. And the same could be said for the limit as x approaches 0 of x over tangent x is 1. So if you ever see these, then those will always equal 1 as well. So these are other fancy trig limit identities for us. Okay. All right. So we know how to work out limits algebraically. We know how to plug in the numbers. We now have our trig limits. So for the next examples, we are just going to be evaluating these limits by using any algebraic process as needed. So as you see there, as I listed as algebraic process, rationalizing by using conjugates, multiplying by reciprocals, getting a common denominator, anything that we may need to help us. So you got to whip out that old school algebra tool belt from 1414. Okay. So let's start on number 1. And Ryan will always tell you if he was here, but he's not. Haha. That before you start a limit, go ahead and plug in that limit first and see if it works to save you some time. And if it doesn't work, then it's back to the drawing board. So what happens if you plug in 0 right away?
H in the denominator, and then a 0 in the denominator.
Would it become undefined?
You'll get a 0 in your denominator, but it's not going to become undefined because what is the numerator going to become?
Also 0.
0.
It's also 0, right? You get 0 over 0, which is what type of form? Indeterminate. So if we ever come across indeterminate like we did above, we go back to the original limit and fix it algebraically. But it is always smart to try to plug the number in first, because if you plug the number in and it works, move on, you're done. But if it doesn't, then we have to fix it. So let's go ahead and fix this one. So I'm going to rewrite it, the limit as h approaches 0. And now let's just go ahead and simplify this. 3 plus h squared. What are we going to have to do with that? What's your other fun favorite F word?
What did I come back to?
F words.
Oh, nice.
There's factor and there's
FOIL.
Yay. Look who's back. Ryan, I gave you a shout out.
You
Ryan, I'm gonna drag you back out somewhere. I'm like, you want to help me with something?
If it's the same problem, I'm gonna lose my mind.
No,
I'm
it's
just kidding.
not.
You're co-host, Ryan, so I think you can make the breakout room if you know how to.
I think the
Or if
breakout
not,
room's
I'll do
still
it.
there.
Here,
Yeah,
I'll
the
do it
breakout-
real fast. Oh, breakout room is still there, so you guys can join it.
I don't know how I can assign them to it though.
I think he can just join it, right? Or no? Or maybe I'll click on it. Cole, and you're going to room 1. Bye, Cole. and now you go, Ryan.
All right.
All right. There you go. Okay, perfect. So 3 plus h squared means 3 plus h times 3 plus h. So we're going to use the basic algebra method of FOIL. So we FOIL that out, and we're going to get 9 plus 6h plus h squared minus 9 all over h. Everybody good with that?
Yep.
And now we're going to simplify more. And we have the limit as h approaches 0. What's going to cancel in our numerator?
The 9.
The 9s. And we're left with 6h plus h squared over h. And then we're still thinking algebraically. So what could you take out of the numerator?
The h.
The h. So we have the limit as h approaches 0 of h times 6 plus h over h. And now the h's in the numerator and denominator will
Cancel.
Cancel. And we are at our final step. We have the limit as h approaches 0 of 6 plus h. And what is my limit?
6.
There you go. And that's how we do it. And that's the only way to do it. So what I'm writing on my paper is how your limit solving process should be. You see how I have the limit attached on every single step until I actually plug the number in. If you don't have that, I will take points off on your exams. No ifs, ands, or buts. So you keep the limit notation on there until you actually plug that number in. Good with that? I guess you'll have to be, right? Thumbs up, thumbs up. Woohoo. Okay, let's keep going. Number 2. All right. Let's go ahead and use the original method of plugging the number in first. But if we do that, what's going to happen?
It's indeterminate.
Indeterminate again, right? Because then you'll get 3 minus 3 over 0, 0 over 0, which means we have to go back and fix it. Okay, I'll write it over. The limit as t approaches 0 of the square root of t squared plus 9 minus 3 over t squared. Hey, this looks familiar, right? Because we did it last class, but with a calculator. So today we are going to find it algebraically. So we need to whip out our algebraic methods, and our job is to get rid of this t squared in the denominator. So does anybody have an idea on how to do that?
Multiply the top and bottom by t squared.
Multiply the top and bottom. Close. But if I multiply top and bottom by t squared, this is now going to become t to the 4th.
Oh, multiply the top one to both of them. The numerator.
So
Would you just square
bottom.
both
The
sides?
conjugate.
there you go.
Yeah, I was thinking of the
There
way
you go.
multiply the conjugate.
So we're going to multiply this by the conjugate of the numerator. I did hear somebody say square it. The only issue with that is we cannot square this because this is an expression. It's not an equation. So we just can't randomly square things. So it's a good thought, but we can't do it on an expression. We can only do it on an equation if there was an equal sign. If there was an equal sign. Okay. So we said multiply by the conjugate of the numerator. So remember, conjugation falls under rationalization. So you can rationalize the denominator, and as well you can rationalize a numerator. So what we're going to do is multiply by the conjugate of the numerator, which is going to be t squared plus 9 plus 3 over square root of t squared plus 9 plus 3. Because in reality, what number is this? Anything good, anything over itself is 1. So this is how powerful 1 is. We are manipulating this limit by using a manipulation by 1. We can change 1 into anything we want. And 1 is now going to be turned into the conjugate of the numerator. So we are going to conjugate this numerator, and let's go ahead.
Quick question. Why'd you put
Yes.
plus 3 and not minus 3?
Good, because what is the conjugate? Do you remember what that means?
Not exactly.
Okay, good. So conjugate means the same statement different operation. So if I had a plus square root of b, and I ask you to give me the conjugate of that, what would you write?
Negative a.
Well, it's only a different operation.
Oh, okay. So a minus square root of b.
There you go. And the same could be said going the other way. If it's a minus the square root of b, what would the conjugate of a minus the square root of b?
A plus square root of b.
There you go. So that's what it means to conjugate.
Gotcha.
And the reason we do that is because it will get rid of the radical and it will get rid of that t squared down below. So what we're going to do next is FOIL the numerator and multiply the denominator. But word of caution, do not distribute this t squared into here. Just leave it on the outside. If you distribute that t squared, we're going to have to factor it back out. So just leave it there. Okay. So we move on to our next step. We say the limit as t approaches 0. And now we FOIL. What is t squared plus square root of t squared plus 9 times the square root of t squared plus 9? What does that become?
T squared plus 9.
T squared plus 9. And then you'll have positive 3 square root and negative 3 square root. What's going to happen to our middle term here?
It's going to change to negative.
Well,
It can be 0.
It's going to be 0. The middle term will cancel. So all we have left is this negative 3 times that 3, and that'll give us minus 9. So your middle term cancels. And this is all over t squared times this nasty looking thing. Okay. And now, again, we're almost there. Rewrite the limit because what's going to cancel in the numerator?
9.
The 9s. And you get t squared over t squared times the square root of t squared plus 9 plus 3. And now, simplify more. What else is going to cancel?
T squared.
T squared. Gone, gone. We're left with the limit as t approaches 0 of 1 over the square root of t squared plus 9. That's too big. Plus 3. And what number can we plug in now for t?
0.
0. So you'll get 1 over the square root of 0 squared plus 9 plus 3. And this is going to give us 1 over the square root of 9 plus 3. And what's our final answer?
1 over 6.
1 over 6. Which, when we solved this on Monday, it was the decimal number 0.167. But using a calculator, solving algebraically, that's much more rewarding. Look at that. Isn't that beautiful? Okay. Any questions on that before moving on?
Okay. I don't want to be that person, but I'm going to be. So you mentioned earlier that we have to write the limit as h approaches 0 or t approaches 0 on every step.
Yes.
But when we're reducing it like that, since it's faster, can we just not put it at the end, like on the end when you were reducing it down, how you didn't put it? Or can we just leave it like that on the top and then write it underneath how you did it?
How about just do it the way I have it written?
Which way though? Because you went 2 different ways on both.
No, they're all there.
Answers.
The limit's there, the limit's there, the limit's there, the limit's there. And since I can't simplify anymore, I plugged in 0, so I don't need the limit on these steps anymore.
Okay, so after you plug it in, then you don't have to keep writing it. That's what I was asking. Okay, sorry.
Exactly.
Thank you. Thank you.
I got a question. What did you do with radical 9? Wait,
What's that?
what to do with 9? Radical 9. Wait.
Radical 9. What is the square root of 9?
Oh, never mind. Wait.
Got it? Cool. Cool. What else? What else? Let's tell them about proper limit notation, Ryan.
Yeah, if it was me, I would be taking our points.
For not attaching the limit to the final steps.
Yeah.
Ooh, tough. I thought I was tough. Okay, perfect. All right. So now we get into a trig limit. Yummy. All right. So number 3. Find the limit as x approaches 0 of sine of 7x over 4x. Now this should start setting off bells. What does this look like?
Oh, 1?
Almost 1. I'm saying more of our limit identity is what we're going to call it, right? What is the trig limit identity that we know?
That's sin over x. Sin x over x equals 1.
Good. So, does this look almost like that one?
Yes.
Yeah.
Yes. Very similar, but we have to fix this one in order to get that one. So, one of the ways to do this is, well, if you look at our limit identity, whatever value of x is inside the sine function has to be the same value of x in the denominator. So let's say if I had sine of 5x, then in order for this limit to be 1, the denominator would also have to be 5x.
Would we just multiply by whatever the denominator is?
Good. So, well, not by the denominator on this one. So here we have sine of 7x over 4x. So this, oops. So this sine function has 7x inside. So this means that in order for us to get 1, we need to have what number in the denominator as well?
The 7.
7x.
The 7. Well, we need a 7x, right? But we need to get a 7 down there. So how could I go about getting a 7 in the denominator?
Multiply by 7 on the denominator and numerator.
Good. So we're going to multiply this by 7 over 7. Because once again, we are manipulating by what number?
1.
1. So this will become the limit as x approaches 0 of 7 times the sine of 7x over, and I'm going to keep this written as 4x times 7. So we just manipulated by 1. We multiplied by 7 in the numerator, 7 in the denominator. Now we have some rearranging to do. So, and the rearranging is going to be in the denominator. So I have the limit as x approaches 0 of 7 sine 7x. What is another way I could rewrite the denominator?
Just switch them. 7 times 4x, right?
Well, it's 4x times 7 right now, and 7 times 4x would be the same thing. We need that x attached to the 7. So what could be another way to rewrite this?
4 times 7x.
Good. 4
Oh.
times 7x. Do those not mean the same thing?
Sure looks like they do.
We can rearrange these because these terms in the denominator are all connected by what operation?
Multiplication.
Multiplication. All right. So there's
Probably we're thinking that was a trick question.
right.
Same.
So there's an associative property of multiplication. So I'll just say associative property. So we can have A times B times C, which is equivalent to A
Times C times,
times B times C. Well, I guess I should just make those look like dots instead.
Yeah, dot products.
Dots.
Going into your cross product. You goon.
There you go. Dots and X's. So just because they're connected by multiplication, we can rewrite them as such. So does that make more sense now?
Yes.
Mind-blowing, right? Okay. And then I'm going to use another limit property here. I'm going to take these 7/4 and move them where?
Outside of the limit.
Outside of the limit. So now we're going to get 7/4 times the limit as x approaches 0 of the sine of 7x over 7x. And now I ask you, does this look like this?
Yes.
Therefore, if they look exactly the same, that means that the limit of sine of 7x over 7x is going to become what number?
1.
1. Oh my. Oh my
Solve
goodness.
that with calculus.
Woo! That becomes 1, meaning our final answer is just what fraction?
7/4.
That's it.
That was fun.
Man,
I
good
think I'm
stuff.
starting to realize that I overthink a lot of things in math.
All students overthink. That is your downfall. No. For math, you just, don't second guess yourself. Be confident in your answer. Be as confident as you can in your answer.
I'm still very suspicious though. This is a little too easy for me.
Graph
Oh
it.
I don't
my
believe it.
goodness. Then hold on to your horses.
One thing you can always do is graph it. Like solve the limit algebraically, graph the function, and see if your solution matches the graph.
Yeah, we've shown all methods so far on how to actually solve a limit. So on Monday, we learned how to make an XY chart. You guys should know how to graph functions in your calculator already. And 3, you now know how to solve all of these algebraically. So there should be no second guessing. There should just be checking. All right. Any questions on that one before moving on? Did it look like magic?
Yes.
It definitely was.
Newton was a wizard.
Wizard. All right. So for this next trig limit, it's actually number 4 is it's asking us to prove that the limit as theta approaches 0 of cosine theta minus 1 over theta, it's asking us to prove that this limit does in fact equal 0. So we are going to start off with a left-hand proof. You guys remember trig proofs, right? Those were great. We're going to start by proving this identity by proving this from the left side. So I'm going to rewrite it and say the limit as theta approaches 0 of cosine theta minus 1 over theta. And one way to start to try to prove this is plug in what number?
0 for theta.
0. So let's see what happens when we do that. You get cosine of 0 minus 1 over 0. What is cosine at 0?
1.
1. You'll get 1 minus 1, which will give us 0 over 0, which gives us what type of form? Indeterminate. So that means we have to fix this algebraically. So our job is to get rid of that theta in the denominator. And if you guys remember trig identities, what was one of the main methods you used to help prove trig identities?
Sine theta.
Reciprocal identity, wasn't it?
You could do a reciprocal identity, but I don't see any reciprocal identities here.
Like sine theta minus cos. theta.
Conjugate.
So this is very similar to the second problem we worked on today. So here we're trying to get rid of that theta, right? So if I go back to that, where is it? Right here. This is very similar to this one. We had to get rid of that t squared. So what did we do to the numerator on this number?
Multiplied it by the conjugate.
Multiplied it by the conjugate. So I know when you guys did trig identities, you used the conjugate a lot, which is what we're going to do to this limit. In order to get rid of that theta, we're going to multiply this trig expression by the conjugate of the numerator. So that means for this one, we're going to multiply by cosine theta plus 1 over cosine theta plus 1. All right. So like I said, we're whipping out all the tools from your algebra tool belt and with a little pre-cal involved. Okay. So we are multiplying this one by the conjugate. So that means we have to get ready to FOIL the numerator and just leave this theta times the outside of that denominator. Do not distribute that theta. Okay, let me minimize that a bit. And then we're going to get the limit as theta approaches 0. And now let's go ahead and FOIL the numerator. If I FOIL the numerator, what am I going to get?
Cosine theta squared minus 1.
Cosine theta squared minus 1 over theta times cosine theta plus 1. Okay, perfect. And now, from this step, what else could we do? What does this piece look like?
Squared
Doesn't
theta.
it equal like 1 minus sine squared theta or something like that?
We're getting there.
Negative
So-
sine
There it
squared,
is.
right? Or theta squared, right?
You got it. You got it. So remember this identity? Sine squared plus cosine squared equals
1.
1. And if you rearranged all of them, you'd get sine squared equals 1 minus cosine squared and the other way around. Well, 1 minus cosine squared almost looks like this, but what's the difference here?
The 1 is negative.
The 1 is negative. So how could we rewrite this to look exactly like that? What could you
Factor out
multiply,
negative
divide
1.
by? Good.
Mul-
Divide by negative 1 or multiply by negative 1. Doesn't matter. You'd get negative sine squared theta equal to cosine squared theta minus 1. Now, do we have an identity going for us? You're like, oh man,
Yeah.
I didn't think pre-cal was coming back. And now we get the limit as theta approaches 0 of negative sine squared theta over theta times the cosine of theta plus 1. Oh boy. All right, guys. What else do we have to do here? Do we see something?
This is such a rough problem to give them, man.
It's not that bad. It's using all the limit properties we used today, and it's also using the trig identity that we learned last time. Does anything in this problem look similar, to the trig identity we know of sine x over x? In this case, it'd be sine theta over theta. Do we have something that looks like that?
How can you rewrite the numerator?
Does that look somewhat similar to that identity?
Except the square and the negative. And yes, somewhat.
It looks close, right? So now we have to think of exponential properties. Sine squared means I have how many sines?
2.
2, which means how many limits can I split this expression into?
2.
2. Oh my goodness, we're getting there. All right, guys. So watch this. Now I'm going to rewrite this as the limit as theta approaches 0 of sine theta over theta times the limit as theta approaches 0 of what's left over from the split.
That is sine divided by cos theta plus 1.
Look at that. We haven't done anything wrong. All we've done is split it up. And now I ask you, what does this limit become?
1.
1. This becomes 1. All right, we're almost there. I can just go down here. Sure. So this becomes 1 times, and now what we're going to do on this limit is plug in what number for theta?
0.
0. You'll get negative sine of 0 over the cosine of 0 plus 1. And what is the value of sine at 0?
0.
0. What is the value of cosine at 0?
1.
1. You get 1 times 0 over 2, but none of that matters because all of this is just going to become
0.
0. Oh my goodness.
Say I'm mean.
All that for a 0.
All that. Hey, we already knew it was 0. We had to prove that it was 0. But yes, you will go through some problems that will take a bunch of steps, and then you're going to realize that the answer is either 0 or 1. But that's the fun part about it. You're like, I saw nothing fun in that.
Where's the
All right.
application?
None right now. The application is learning your algebra, learning all your algebra skills back, and your trig identities are coming back to haunt you.
Yeah, I'm getting flashbacks from pre-cal.
Pre-cal PTSD. Okay. Soak that one in, because number 5, I don't know, is it any better? There's no trig involved in number 5, but you have to understand what piecewise functions do, or what absolute values do, sorry. Absolute values, which lead to piecewise functions. See, I give everything away early. Okay, everybody good with number 4? Got a thumbs up. All
Till
right.
next time.
Till next time. Perfect.
They're just like, we're calling class.
They're like, that was enough. He reached into our brains too deep. All right. Number 5. This says g of x equals x squared plus x minus 6 over the absolute value of x minus 2. All right. We want to know what the limit from the right side is and what the limit from the left side at 2 is. All right. So once again, you have to understand what absolute values mean here when we deal with limits. So I'm just going to move to the outside of the page real fast. And let's just talk about the absolute value of x. One thing we know for certain is whatever number you plug into the absolute value of x will always come out positive. But does anybody know that the absolute value is also a piecewise function? Which means that the absolute value of x can be written as, for all values of positive x, this only exists for x values greater than or equal to 0. and negative x for all values of x less than 0. So the absolute value function is also a piecewise function. And if you forgot what a piecewise function is, well, this is a piecewise function. A piecewise function is a function made of multiple outputs with different restrictions. That's all it is. Okay, so now the reason I'm showing you this is because we're going to have to create a piecewise function for this limit problem. So I'm just going to go ahead and take care of it over here on the outside. So what we're given is the absolute value of x minus 2. So in order to create this into a piecewise function, we have to write this as for all positive values of x minus 2. This can only happen when our values of x are greater than 2. And I'll tell you why I'm not putting an equals to on there. And then for the next part, it's going to be for all negative values of x minus 2 for everything less than 2. And the reason I'm not putting a greater than or equals to symbol is because x minus 2 is located where on our function?
The denominator.
And what number can never ever be in the denominator?
0. Well,
0.
in this case, 2.
Well, if we plug into, the denominator would become 0. Therefore, that's why I don't have a greater than or equal to on it. Okay. So now we are going to learn how to match limits to a piecewise function. So we have to understand what a left-hand limit and a right-hand limit do, or what is the definition of a left-hand and a right-hand limit. So for the very first function, or first question, it says, find the limit of g of x as x approaches 2 from the right side. So let me just go ahead and rewrite this. It says, find the limit as x approaches 2 from the right of x squared plus x minus 6 over, and I'm not going to fill in the denominator just yet, because here is where we are going to connect a limit to a piecewise function. So remember, if my limit is approaching from the right side, does that mean that my values of x are going to be bigger than 2 or less than 2?
Greater than 2.
Greater than 2. Because remember, if you ever have a limit coming from the right side, this means all the x values are going to be greater than that number you are approaching. So since this limit matches up with this restriction, this means we get to use the output of x minus 2. And now that's what I'm going to put in my denominator. So the limit matches to the piecewise, which tells us which output we can use. So now my denominator is going to be just x minus 2. Everybody good on that? I can run it back if you need to.
Yes. Can you? You lost me.
Okay. Run it back. Run it back again. Okay. So going over it. So first we're looking at the limit. This says the limit as x approaches 2 from the right. So if I were to draw a graph, here's 2. If we approach 2 from the right, this means we're coming from positive infinity, right? Which means that every number to the right of 2 is going to be greater than 2. So that means that this limit matches this restriction, because what does that restriction say? X has to be what?
Greater than 2.
Greater than 2, which means that it matches the limit 2 to the right. And if we match to that restriction, this means that we get to use this part of the piecewise function. which goes exactly right there. Make a little more sense?
Yeah, so if it was from both directions, would we have 2 limits to solve?
Hey, which is down there. We'll get there in a
Oh, okay.
second.
Okay.
Good question, though. Very good question. Okay, so that's why you have an output of x minus 2, because it's a limit from the right. And now we want to evaluate this limit, which means what number are we going to plug in for x?
2.
2. But what happens if we plug in 2?
You get 0.
You get 0. Oh my goodness. So this means that we're not even to plug in 2 right now, which means we have to look at the numerator. And what can you do to the numerator?
Factor it.
Factor it. What does the numerator factor to?
X minus 2x plus 3.
X minus 2, x plus 3 over x minus 2. And what happens to your x minus 2s?
Cancel.
Cancel. And we are left with the limit as x approaches 2 from the right of x plus 3. And what is my limit going to be?
5.
5. Good. All right. Everybody good with that? Because now we're going to do it again from the left side. So here we go. We are approaching 2 from the left. And if you approach a number from the left, are you greater than or less than?
Less.
We are less than. Meaning my denominator is going to be what now?
Negative parentheses x minus 2.
Good. So we approach 2 from the left. We already know the numerator factors, so let's go ahead and do that. X minus 2, x plus 3, but now since my limit, once again, my limit matches to that restriction, our output in the denominator is negative parentheses x minus 2. So negative parentheses x minus 2, and just like the above, your x minus 2's cancel. And you're left with the limit as x approaches 2 from the left of x plus 3 over negative 1. And what is my limit value here?
Negative 5.
Negative 5. Good. Okay, everybody good with that? Javier with a thumbs up today. Thumbs up, thumbs up, thumbs up. All right. So now C. C is not asking us to look at the piecewise or the restrictions. C is asking us if the limit from both sides exists, which will fall on that theory, the existence of a limit. In order for a limit to exist from both sides, the left hand must be equal to the right hand. In this case, what is the left-hand limit?
Negative 5.
What is the right-hand limit?
5.
Are those equal?
No.
No. Therefore, the limit as x approaches to what?
Doesn't exist.
Does not exist. There you go. And that was a small lesson on piecewise functions and absolute values.
I have a question.
Go
So if we run across an equation like this with the absolute value, like in the denominator, right? And it asks us if does the limit of g of x exist, right? Does that mean we would have to do A and B?
Because
to find
most
it?
likely your homework is going to be set up for you to answer the first 2 questions, no matter what. So you're going to have to get there to get to the final one. No shortcuts, right? Even if you know it doesn't exist, you're a math major. You have to prove why it doesn't exist. Not just because you've seen it through memory. Computer.
Yeah.
All right. Everybody good with these? Thumbs up. Thumbs up. Amanda. Thumbs up. You have a brown thumb, Amanda.
I don't see the problem with this.
Me neither. All right. All right. Last two questions. Perfect. I'm going to give you guys, we got a lot of time. Let's say 5 to 10 minutes, and I'll let Ryan solve the last two questions.
Oh, yeah.
Yeah.
Oh yeah, brother.
Yeah, brother.
Call me the Hulk of calculus.
That's right. So look at them, try to solve them, and Ryan, you can start working on them in 5 minutes if you want, or whenever you want. Don't matter.
I'll just knock them out and then share my screen once it gets to that time.
Hey, there you go. That makes it easier. So yeah, 5 minutes, y'all.
Or do you want me to just write the answer down?
No, I mean, just show all your work and stuff.
Okay.
So you can go through it. Oh my goodness. Hey, nice. They gave us our W-2 forms. Perfect.
I've still been working on that VPN thing.
Well, you don't have to worry about it till next month now.
Yeah, April, it's just like, they'll be calling you today. And I was like, well, shouldn't they ask me when I'm available? And they were just like constantly calling me during my lab today. So I was like, oh, this is great.
Ay, ay, ay. I don't even know what class this guy's in.
Ooh, you get a tax deduction this year.
Oh, for the kid. I know. I already started doing it. I was like, man. I was like, she paid off her hospital debts real fast.
Yep.
It's good to have a kid.
Now to deal with those college
It's like
debts.
benefits and negatives, you know.
Yeah, tax day was a good benefit. It was wonderful.
Yeah, but then how much did it cost to have them? And I'm
True.
just kidding. I love
Like I
my
said,
kids.
it like zeroes out because even after that, they keep spending your money.
Mm.
Exactly. I pay for daycare right now. That's just insane. I'm almost done. She's going to be hopefully in pre-K this fall. That'll save me literally $1,000 a month. Just on her
You're
daycare.
so lucky. We couldn't get my daughter into a pre-K program, so we're still paying for like her preschool pre-K program. So fall, she goes into kindergarten. I'm so excited.
Oh, I told her. Well, I mean, I didn't tell her. I told my husband. I go, if she doesn't get into pre-K here, I'm hoping she does. If she doesn't, I go, we're keeping her, and I'm saving that money. There's no way I'm paying for daycare anymore after August. It's insane.
I got you.
Yeah.
If you're in San Antonio, you get pre-K for SA. We're in Bexar County, so we don't qualify for it. So
I think you could do pre-K for SA, but you have to pay tuition for it.
Well, I'd still have to pay.
Yeah. Yeah, but it's not as much. I mean, it's like way less than normal daycare is, but yeah, it's still a lot though. It's crazy.
Not looking forward to that. I hope we stay remote forever. Daycare is free.
Yeah, but then your kid's gonna turn into like some weird antisocial, doesn't know how to interact with other
Oh, for
humans.
sure. She's gonna be like, "Hi, my best friends are my parents." That's right.
And Uncle Tap.
Uncle Ryan, Uncle Aaron Tap. All right, go ahead, Ryan. I think it's been 5 minutes.
I'm almost done. Hold up.
Oh gosh.
I'm trying to be as neat as I possibly can. I think this is the cleanest handwriting I've ever done for a problem.
Marvelous.
Indubitably.
Lois.
Harry Potter.
Harry Potter.
Oh, wait, what am I doing?
Before he shows it, I guess if everybody else is maybe done, can I share my answer, see if I got it right before I see everything else?
Sure.
Yeah, sure.
Sure.
So the first one I got 3. And then the second one I got 1/12.
I think that's right.
That's right.
Yeah. Nice.
I got 3, but the second one I got 4.
Uh-oh.
Make sure you factored that denominator.
I think I might have been.
Big reveal.
All right. All right. So there's your number 6. All you had to do is multiply it by 3/3. And then you get that trig identity, sine 3x over 3x. As x approaches 0, that becomes 1, and your answer is 3. Any questions on that one, guys? All right. And then the last one. I hope you remember how to factor a sum of cubes. If not, well, you're probably on a computer, so you can Google it, right? Sum of cubes. Factor a sum of cubes, which is what Ryan did. X cubed plus 8 factors to x plus 2 times x squared minus 2x plus 4, where your x plus 2's will cancel, leaving you with 1 over x squared minus 2x plus 4, where it's now safe to plug in -2, simplify, and you get 1/12. Any questions on that one? Like, was I supposed to keep the sum of cubes on me at all times? Yes.
Gosh.
Yes. Okay. Well, look them over. If you're still working, great. Other than that, if you have questions on the notes, on the homework, ask away. Other than that, we are done.